Okay, first of all, I'd like to thank the organizers, Uemura Sensei and Bianconi Sensei. And today, I'd like to talk about the BCS-BEC crossover in iron selenium sulfur superconductors. So this work has been done in collaboration with many people listed here. But main player are the Yuta Mizukami and Ohei Tanaka in our group in the University of Tokyo, and also the Dr. Hashimoto from the Professor Shin's group who have done the laser RPS measurements. Okay, so let me start with the introduction on the BCS-BEC crossover. And I'm sure you have seen this kind of phase diagram many times during this conference, but here is the temperature divided by the film temperature as a function of strength of attraction, okay? And in the weak coupling limit, we have a BCS state, of course, as you know. And here, the pair size or coherence length is much longer than the inter-electron distance, which is of the order of 1 over kF. So we have a situation that the kF xi is much larger than unity. And in the opposite side, we have a strong coupling limit. So we have a Bose-Einstein condensation limit. Here we have this kind of tightly bound molecules, and in which pair size is much smaller than 1 over kF. So kF xi is much smaller than unity. And if you look at the electronic structure, and let's suppose we have one hole band, as shown by the red curve, like this. And what happens in the BCS state, in the superconducting state, below TC, we have actually gap opening at Fermi wave vector kF. This is, as you know, right? But in the case of BEC limit, what happens is that the chemical potential becomes negative. So the minimum gap opens at k equals 0, not at k equal kF. So we have this kind of convex up curvature in the superconducting state. Now, an important point here is that we have no phase transition between these two limits, so we have a crossover. And the most interesting part is the so-called unitary limit, and where we have a strongly interacting pairs, and the kF xi is of the order of unity. And one important parameter here is the ratio between the superconducting gap delta and the Fermi energy EF, which this ratio is related to the 1 over xi kF. In the case of conventional superconductors, as you know, this delta over EF is very small, like 10 to the minus 4 or minus 5. But in the case of underdoped high TC cuprates, this ratio becomes quite large. And there is a big discussion about the relevance of this BCS-BEC crossover physics in underdoped high TC cuprates. And in this context, I would like to show you that this iron-based superconductors, iron selenium, is a key material to investigate the BCS-BEC crossover physics. And this material has a very simple structure, like you have just layers of iron selenium like this. And we can get very high quality single crystals by using the chemical vapor transport technique. And it has a very interesting physical properties. First of all, this is a temperature dependence of resistivity, and you have a kink at Ts, which is 90 Kelvin. And this is the structural transition from a tetragonal at high temperature side to the orthorhombic in the low temperature side. And we have no magnetic ordering down to low temperatures, which is quite different from the other iron nuclide superconductors. So, and below Ts, we have a strong in-plane anisotropy occurring. And for example, if you look at the vortex cores, it has an elongated shape along the A-axis. And so we call this state as a non-magnetic nematic phase below Ts. And we have also superconductivity at 9 Kelvin without any doping. And if you look at the electronic structure, it has a very interesting thing. And we have a compensated semi-metallic electronic structure, which means that you have equal numbers of electron and hole carriers. And we have a very small Fermi energies. That is the key to the BCS-BEC crossover. And the electronic structure can be investigated by the quasi-particle interference by using STM technique, which has a very high energy resolution. And depending on the Q direction, we can see the electron-like dispersion like this, or hole-like dispersion like this, from which we can estimate the Fermi energies of this electron and hole bands. And at the same time, this technique can give you information about the superconducting gap, delta. So we can get the information of the delta over EF for these two bands. And for the electron band, we get the delta over EF of the order of unity. It's almost like more than unity, okay? Which is very large. And for the whole band, we get delta over EF about 0.3. So these numbers are quite large, much larger than the other superconductors. And we can also get the information of the KF and Gzi from the upper critical field measurements. And we get the number of Gzi KF, which is of the order of unity. So we can kind of safely say that this iron selenide is located deep inside the crossover regime between the BCS and BEC limits. So this is a quite important material to look at this BCS-BEC crossover. And one important thing is that the so-called pairing temperature, which is deviate from the TC in this side. And we expect the extended temperature regime in which we have the so-called preformed pairs. Or you may expect the sort of pseudo gap. So we want to look at the evidence for the preformed pairs, first of all. So to do this, we want to quantify the magnetic signal, and we measure the magnetic torque, which has a very high sensitivity by using this kind of micro-cantilever technique. And the sensitivity is much higher than the commercial squid magnetometry. So what we can do here is that we can rotate the magnetic field like this and measure the torque as a function of angle theta, which is from the c-axis. And you can see this kind of sine 2 theta curve like this, and the amplitude of this oscillation is proportional to the difference between the c-axis and a-axis susceptibilities. So we call this difference as delta chi. And here is a plot of temperature dependence of delta chi. And as you can see, we have an anomaly at the structural transition at TS, which is expected. So we can plot the temperature dependence of the magnitude of delta chi at different fields. And as you can see, below about 20 Kelvin, which we call T star, it starts to have a strong field dependence. And this strong field dependence should come from the superconducting fluctuations, which is actually diamagnetic susceptibility signals. And we can analyze these superconducting fluctuations by comparing with a conventional Gaussian type fluctuation. And this is given by this kind of Asramasov-Larkin type expression. And we compare our data with this theory curve. And as you can see, these theory curves deviate from the experimental data. And our data shows a much larger diamagnetic signal than the expected by the theory, okay? And I should mention that this theory curve is for the zero field limit. And as you can see, we have a tendency that if you go to lower fields, it gets more enhanced, meaning that our data suggests that we have a quite giant superconducting fluctuations compared with the conventional Gaussian type fluctuations. So these giant superconducting fluctuations are a signature of the BCS-BEC crossover, which is supported by the recent theoretical paper by Adachi and Ikeda. Okay, so far so good. So we have evidence for BCS-BEC crossover in this material, but we pose a question. What about the specific heat, which is the most fundamental thermodynamic quantity? And here is a very simple comparison between the S-wave BCS superconductors and the simplest BEC, which is the 3D Bose gas. Okay, so let's look at the C over T as a function of temperature. And in the case of BCS superconductors, as you know, we should have a jump at TC, right? Because we have a second of the phase transition. And in the superconducting states, it depends on the structure of the superconducting gap, but if you have a fully gapped state with no nodes, then you should expect the exponential decay at low temperatures. That's you know, right? However, in the case of BEC, what happens is that C over T shows a gradual increase in the normal state towards TC, and we don't see any jump at TC. But we have a kink like this. And in the superconducting state below TC, we have a power law dependence. In this case, C over T is proportional to the square root T. Okay, so we want to look at this problem. And so we actually developed this kind of homemade calorimeter, which we have a very small addenda component, much smaller than the commercial PPMS type thing. So we can measure the very specific heat very precisely for small single crystals with a mass of less than 100 micrograms. And we use the so-called long relaxation calorimetry technique, and we make a large pulse, and we acquire many data points up to 10,000 or 100,000 data points to give the information on the temperature dependence of the specific heat. So this is an example for iron selenium. So we use the very small single crystals because we want to use the very pure single crystals. And this is, the sample is about 81 microgram, which we can compare with the previous measurements, which have much larger single crystals. And as you can see, our data shows very consistent results with previous ones, and it shows a clear jump, right? So we can say that this is typical BCS type temperature dependence of specific heat, right? Even though we have a situation that the delta over EF is close to unity. So what's this, right? That's the question. So I think one has to consider the effect of multi-band electronic structure. And also there is a talk by Carlos this morning. The multi-band effect on the BCS-BEC crossover is a non-trivial effect. And I think there is this paper, Chubukov-FMOP, gives a very important contribution to this problem. And what they found is that they consider one hole band and one electron band as shown by this dashed red curve, like this, in the beginning. And they consider very strong interband interaction between these bands. And then they put the delta over EF large number, and they calculate the electronic structure like this. And in the case of single band, as you expected, you can have this kind of BEC-like state. So the minimum gap opens at k equals 0. However, in the case of these two-band systems with the strong interband interactions, what happens is at least one of the bands shows like a BCS type electronic structure. So the gap opens at kf, not at k equals 0. So I think this may be a relevance to our data, suggesting that if you have strong interactions between two bands, you may have a BCS-like state, even if we have a large delta over EF. So we want to look into this problem further, and we want to look at this system. This is iron, selenium, sulfur. So we substitute selenium with the isoelectric sulfur like this. So this is a set of temperature dependence of resistivity data. And as you can see, we can assign this nematic phase transition as a kink. And we can construct a phase diagram like this. And the nematic phase transition temperature goes down. And above 0.17, we got a purely tetragonal phase like this, okay? And actually, Hanaguri-san, my colleague, can look at the STM topographic data like this, and he can assign this position of sulfur by looking at this STM. And he can look at the wider view, and he put the points on the positions of sulfur, and as you can see, there is no evidence for any segregations, meaning that we have quite homogeneous single crystals. And also, we have observed quantum oscillations in a wide range of the sulfur content, meaning that we have a very clean crystals. So I think this is a quite good system, homogeneous and clean, to look at this BCS-BEC crossover physics. So let's look at the specific heat data as a function of X. So again, this is the iron selenium, so X equals 0. So in this phase diagram we are looking at here. So we are deep inside the nematic phase. So here I plot the electronic part of the specific heat, Ce over T. So we subtracted the phonon term as a function of temperature. And as I said, we have a clear jump at Tc, which is like BCS. Okay? Now we go to a 10% substitution, and we still have a Ts, which is like 60 Kelvin. So we are still deep inside the nematic phase. And again, this C over T shows a large jump at Tc. So we are still in the BCS-like state. However, we were very surprised to look at this data, which is at 20%, which is in the tetragonal side. Okay, so we have no nematicity here. Okay, and so C over T shows a gradual increase towards Tc, and shows no jump, but we have a kink at Tc. And if you plot the C over T as a function of T, square root T, then we got a straight line below Tc, meaning that here we have a temperature dependence of square root T. So this kind of feature is surprisingly similar to what is expected in the BEC case, and actually most simplest 3D Bose gas case. So as you can see, you have a gradual increase, and you have a square root T dependence just below Tc. Okay. So here's again the comparison. So this is the iron selenium, which is in the nematic phase, and here is the 20% sulfur doping, which is in the tetragonal phase. You see the quite difference. Now we can also take a look at the tunneling spectra. So this is the measured by STM again, and here the blue curves are in the nematic phase, in the low concentration side, and the red curves are for the tetragonal side. Okay. First of all, in the nematic phase or orthorhombic phase, we see a clear coherence peak, quasi-particle peaks. However, if you go to the tetragonal side, everything seems to be smeared, and we have a much smaller gap. And it's not clear from the figure, but we have a finite zero energy density of states in the tetragonal phase. Okay? And this zero energy state is quite consistent with this C over T data, because this data has taken at 0.4 Kelvin, which is around here. So as you can see, we see a quite remarkable large density of states, C over T, even at low temperatures. So these two data gives a quite consistent picture. So from this, we kind of conclude that this data shows a thermodynamic evidence for possible BEC-like state in this material. And I think this is the first thermodynamic evidence for any kind of solids for the BEC-like state in the superconducting system. Okay, so we can also measure the torque, magnetic torque. So this is again the delta chi as a function of temperature at different fields. And as you can see, we see a large field-dependent component. So we have a large superconducting fluctuations And this solid line is the, what is expected from the Aslama-Sobraki conventional Gaussian type fluctuation. So we have a strongly enhanced superconducting fluctuation again. And the magnitude of this deviation is much larger than the iron selenide. So this is, again, consistent with the BEC-like state in the tetragonal side of iron selenium sulfur. Now, my colleague, Professor Shin's group, have measured the 7 EV laser outputs in this system in the 2 Kelvin, which is below the TC in the superconducting state. And the overall feature is shown like this, and it has a very flat dispersion. So actually, they are looking at near the gamma point. So in the normal state, we have a kind of single hole band near the gamma point. But in the superconducting state, we have a very flat dispersion like this. But if they blow up this part, low energy part, what they found is that we can see a kind of still a convex down features in the orthorhombic phase. So the minimum gap occurs at KF. And, but if you go to the tetragonal side, it shows like a convex up features, okay? So this is, again, consistent with the BEC-like state in this tetragonal side of the iron selenium sulfur. Okay, so then the question is, what about delta over EF, okay? And from the quantum oscillation measurements, we see that the frequency, which is proportional to the cross-sectional area of the Fermi surface, is going up, is increasing X. So meaning that we are actually increasing the Fermi energies if you go to right-hand side. And at the same time, the TC is going down here. So meaning that the delta over EF is actually becoming smaller than the iron selenium. Okay, so this means that the observed BEC-like state in the tetragonal side is quite unexpected because we have a small delta over EF, right? So this immediately implies that we should have another key parameter that determines the crossover rather than just delta over EF. Okay. So, of course, this is a very important but unresolved question, but one possible scenario is that we should, again, consider the multiband effect. And also, we need to consider the pairing interaction. And we have 2 kinds of pairing interaction. One is the intra-band interaction and interband interaction. And that also have been discussed by Carlos this morning. And actually, Ilya Eremi and his co-worker have calculated the pairing temperature and actual TC as a function of the ratio between the intra-band interactions and interband interactions. So if you have dominant interband interactions, this TC and T pairing becomes closer, meaning that you are in the BCS state. But if you increase the intraband interactions, what happens is that you have a quite deviation between these 2 temperatures, meaning that BEC-like state becomes more favorable, okay? So this suggests that, this ratio between the intraband and interband interactions may be a key parameter to determine the BCS-BEC crossover in this kind of multiband system. So experimentally speaking, it's quite difficult to quantify these interactions, but one can say something from the phase diagram. So this is the temperature versus sulfur content versus physical pressure, 3-dimensional phase diagram we have obtained recently. And if you look at the iron selenium, right, then you can, if you apply a physical pressure, then you induce actually the magnetic order. This is the stripe-type magnetic order, which comes from the strong interband interaction between hole and electron bands. But this onset of magnetic order is shifted towards higher pressure side if you increase the sulfur content. So this is actually consistent with the fact that we may have a smaller interband interaction in the sulfur-doped iron selenium. So this is in line with the idea of the Ilya-Elmin and cobalt case. Okay, so let me summarize my talk. So this is the kind of phase diagram we have obtained. So we have a nematic phase transition line coming down like this. And here in the nematic phase, we have observed the evidence for BCS-BEC crossover, meaning that we have a large delta over EF, and we have signature of the large superconducting fluctuation here. But if you go into the tetragonal side, first of all, the TC gets lower, and delta over EF becomes smaller. However, we get evidence for BEC-like state, which is very unusual, okay? And we suggest that maybe the interband or intraband interactions, the ratio between these two may be an important key parameter. But I would like to stress that this is a very good Baroque system. I think the first solid system for studying the multiband BCS-BEC crossover. Thank you very much for your attention.